Hi, my name is Pop. I'm a researcher at Ethereum Foundation, and this is Daniel, our Ethereum protocol fellow. Today we are going to talk about network simulation. Before talking about the network simulation, we have to know first like why we do simulation at all, right? From our experience, we usually have like two common use cases. Like the first one is like, for example, if you have like the protocol idea and you are not sure like if it's good or not, right? And maybe you want to test it first. So you have to run the simulation. The second one is like, for example, if you have the hypothesis that okay, maybe you have the illusion that is good already, but you are not quite sure yet. Maybe you want to run the simulation like to confirm your idea. Right? When you do the simulation, usually the input usually be like you have to have the protocol implementation first, right? Otherwise, you cannot simulate it. The second one is like you have to have the network topology in mind, like how much bandwidth each link have in the network, right? Or like how much is the latency and like how much is the packet loss rate, right? And you have to make the network topology like as similar to the real world as possible. Otherwise, like the simulation doesn't make sense at all, right? And the output of the simulation, what you usually want from the simulation is like you want the metric like the number of reauths or message propagation time, and in fact it can be anything that you want that you are not sure that what it will be like before the simulation. Before talking about like how we do the simulation, I want to talk about like how we do the simulation like previously. And previously, what we usually do is like we run the client inside like the physical machine, and then we use something like NetM to emulate the link. Like maybe you want some like bandwidth on your link, like you just use NetM, or maybe you have the latency that you want, you just use NetM, and you just run it in the physical machine. And that doesn't work, right? Because it doesn't scale really well. Like when you run like a lot of nodes inside a single machine, they will compete for the CPU, right? And that is bad because the timing will be like inaccurate, right? Yeah. And like I think you can just run a few nodes like inside a single machine. So what you will do instead is like you have to have like a lot of machines to simulate, right? And that is like a problem because it doesn't scale. There is something called like discrete event simulation. The discrete event simulation is like instead of running the client inside the machine like directly, you run it inside a simulator, and the simulator will process and create the event. Like for example, when you send the message to network, right, and that's a kind of an event, and when you receive the message from the network, that also the event. Is like instead of running it in the machine, it will just capture and process the event. It's good because the clock in the simulation will be independent from the real clock. So yeah, I will tell how it works like later. Yeah, because the node don't have to compete for the CPU anymore, so you can run like any number of machine inside a single machine, and you will get the quite good simulation result. And we have a problem with the existing discrete event simulator because like NST or Omnet, when you do the simulation, you have to call the library of the simulator. And that's the problem because when you have to call the library, you cannot implement the protocol like in any language, right? You have to implement it in a supported language that the simulator support, right? Because you have to call the library. Like calling the library to send the message and like receive the message, something like that. Yeah, but we found that there is a great simulator called Shadow that doesn't have this problem. The shadow is instead of forcing you to call the library, what it does is like it will intercept the system call that the client make, right? And like so by doing this, you can implement your protocol like in any language because and then run inside like Shadow. Yeah. So for the example of the system call that it will intercept is like the send system call or receive sender call. Yeah, and that's as I mentioned earlier, is a kind of an event. And another important thing is like the get time of the day, because we intercept the get time system call as well. So so you can tell your client like what time it is, right? So that is why the clock inside the simulation is independent from the real clock, because Shadow will tell your client like what time it is. So that's quite great. Yeah, so in short, Shadow can simulate like a lot of nodes, right, with the real client software, because you don't have to implement like in some specific language. You can implement it in any language, and then you just run Shadow with your client, and then in fact you don't have to modify the client at all. You just use your client and let the Shadow intercept the system call. And we implement something called like each Shadow, because Shadow work with like any kind of software, but not specific to the Ethereum client. So we create something called eShadow to let you run the simulation like easily. You just like tell what client you want to use and like how many nodes, how many and then you just run it easily. Yeah, the next is we are going to talk about like eShadow. Let Daniel talk about it.
Thanks, Bob. Hi, I'm Daniel. And over the past few months, we've worked on eShadow, which makes it really easy for anyone to run shadow simulations, including Ethereum clients. So in one sentence, it is basically a configuration generator that makes it easy to simulate Ethereum networks in Shadow. It has a couple of features. First of all, it has a rather simple YAML configuration format, so you don't have to learn anything fancy. It allows you to simulate realistic geolocation and network reliability. It supports Geth, Lighthouse, Teku, and Reth right now, with more planned. Hopefully soon, or at some point, supporting all clients. It allows us to capture client metrics, which is nice for analyzing the simulations after they've run. And it allows you to run your own programs as well, if you want to simulate some malicious nodes or some attack scenario. Finally, it scales well, so you can run simulations with over 100 nodes on your laptop. So Ethereum, as you know, is a huge distributed network, and it's globally distributed. Yeah, there are like a lot of nodes in Europe and North America, but also a few in Australia and East Asia and South America, etc. And for simulating such a network, to figure out future changes to the Ethereum protocol, it is important that we can simulate the fact that we are distributed across the globe. So here you can see a configuration sample of eShadow. On the top, you can see we define the first node, which is located in East Asia. It also sets a reliability, which I'll get into soon. And on the bottom, you see that we define 10 more nodes in Europe and NA East, and also North America East. And it will distribute those 10 nodes across these locations. Yeah. Home stakers are very important to Ethereum. Like, we want to be decentralized, so we want people to run actually nodes and validators at their homes. But the problem, or the fact with that, is that those nodes often have not as good of a network connection like something running in a server farm. And we can reflect this in the simulation by specifying a reliability. The top node is marked as reliable, which has a gigabit of bandwidth, no added latency, and no packet loss. But the bottom 10 nodes are home nodes, and they have restricted bandwidth, a bit of added latency on top of the geographic latency, and also a tiny bit of packet loss. yeah, you can define your own reliabilities and locations if you really need them, or just use the predefined ones for convenience. Clients. As mentioned, right now we support Geth and Lighthouse, which is like first-class support right now, and there's also support for Reth and Teku, which is currently in testing, and it's pretty easy to run mixed client stacks. Again, we extended the configuration. On top, you can now see we have Reth and Teku, and on the bottom, we use Geth, Lighthouse, and the Lighthouse validator client. And that's all you need to do for ETH Shadow to configure these clients and distribute the configured validators across the validator clients in the simulation. We also support some other software. For example, in the bottom, you can see Prometheus, which will automatically be configured to receive all the metrics from the consensus layer clients. We have a purpose-built blob spammer because I did some simulations on PeerDAS, and for that we needed a blob spammer. So yeah, it's also pretty easy to use, but omitted on the right here. And also, you can configure your own program. So if you have a modified version of Lighthouse, for example, which does something malicious just to test, you can configure it as well. Supporting more clients. Well, to be a really useful tool, it would ideally support all the Ethereum clients. However, this is not currently the reality, because unsupported clients use an unsupported Linux system call, like unsupported by Shadow, or get stuck in a spin lock, which Shadow can't really cope well with, or it uses a supported Linux system call, but the implementation in Shadow is a bit different than the actual implementation in Linux. And Shadow supports currently 186 of approximately 375 Linux system calls. That's a lot of system calls. And only 4 of approximately 80 socket options that you can set when you are opening a TCP socket or UDP socket. And to support all programs, we would have to implement all these system calls and socket options perfectly accurately, which is really hard to do and not really feasible to do on short notice. So we need to kind of pick what we need. We could also just modify the clients that are running in the simulation to avoid those system calls, or do not set this socket option. But that is also not kind of nice, because we don't want to maintain forks of clients indefinitely to support them in Shadow. So yeah, we have to implement these missing features in Shadow instead, which will take some time. Simulation size. So our claim is that we can run simulations with over 100 nodes on your Linux laptop. But before we get to that, let's look at small simulations. Small simulations with under 10 nodes, for example, run pretty quickly. Like on my system, they ran faster than real time, because as Pop mentioned earlier, Shadow can also manipulate like the get time of day calls or something like that to pretend that time is running more quickly than it is in real life. And as your simulations get larger, of course the CPU time gets congested, and simulations will run smaller. Here are 2 examples. On my system, I usually run simulations with 38 nodes, which nicely fit into my 28 gigabytes of main memory with Rest Lighthouse and a Lighthouse validator client per node. And for me, it took like 45 minutes per 30 minutes of simulated time, so 1.5 times slowdown, which is rather nice. On Pub system, we tested 100 nodes with Geth, Lighthouse, and Lighthouse validator client, 16 gigabytes of memory, and to simulate that many nodes, you will need swap space, so we used 32 gigabytes of swap there. This took far longer, 11 hours for 10 minutes of simulated time. So it is possible to run those, but you should probably start with a small simulation to confirm that everything is well, and then just let your laptop run overnight if you really want to have a larger simulation. You can also run really, really large simulations with over 1,000 nodes. as we have retested. And for that, I rented a server, and that had 1 terabyte of memory, and that took, for 45 minutes of simulated time, 4.5 hours approximately. It kind of varied a lot at that point. And also at that point, what I want to note is that at that point, memory speed becomes the bottleneck. So we can't just throw more virtual cores at it and hope it gets faster. No, as Shadow has to switch between these processes a lot, we just exhaust the memory bandwidth through our main memory, and we can't really get faster by having more cores. Finally, I want to point you to another presentation that I held yesterday, where I also present some experiments that I ran with ETH Shadow. So if you want to see what ETH Shadow is capable of in practice, how it can enhance your testing workflow, feel free to scan the QR code. I'm going to leave it on there for a few more moments. And after that, Pop also has something to say.
Yeah, thank you. And actually, the EF research is like looking for a peer-to-peer network expert. So if you are interested to apply, you can like go to our EF job website over there. And for the ETH Shadow, you can also pay with ETH Shadow like at Ethereum/ETH Shadow. Yeah, that's it. Thank you.
Yeah, okay. Yeah, simulate 100 nodes on a single laptop, also in a single YAML file. That's pretty cool, right? I like that. Next time you think about simulating Ethereum network, check out, as you see before, GitHub ETH Shadow. Next up, the Q&A. Please scan the QR code, open Meerkat, right? Go to the bottom right. You'll see the live Q&A there. So click in there. You can create and upload questions there. So we'll go with the first question. Ooh, okay. The first question is, can you scale Shadow horizontally by adding more workers?
I guess the workers mean machine, right? Currently you have to run Shadow inside like a single machine. Theoretically, it's possible that you can run it inside many machines, but it's an open research problem, and we cannot do that now.
Okay. The next question is, what is the difference between ETH Shadow and kurtosis?
I think kurtosis is like a Docker compose, right? And like you have to like when you run many nodes inside a single machine, it will compete, like it will share the CPU, and if you run too many nodes, it will be like too slow, and like the simulation will be like inaccurate. Like I think you can just run like a few, like less than 10 nodes like inside a machine, I guess.
Okay. How do you handle the client's memory and storage requirements when running a lot of them on the same machine?
The storage is not a problem because we don't have like the EL state, so we don't have to have like a lot of storage. But in terms of the memory, as Daniel talked about it, like we use like a 1 terabyte memory machine to run like 1,000 nodes. Yeah, so you have to have a lot of memory.
If I may add to that, we also start with a fresh genesis state, so with a new DevNet, and nodes running on an basically empty state use way less memory than a mainnet node. So like that, we can, like if you think about it, 1,000 nodes on 1 terabyte is 1 gigabyte per node, which is very, very small, but it's possible because we have this empty state.
Okay. The next question is simulation able to capture some edge case flaw in the protocol?
I'm not sure what edge case means. Like, I'm not sure like what case, maybe.
I think it is, because I just mentioned my other presentation. You can also find it in the Devcon schedule. I used it actively to find issues. Well, with the issues with the protocol, it would be also possible to find it there. ETH Shadow, in my opinion, is more suited for network-related things because, it really puts its focus on the network layer. But it's possible that you can configure some attackers that find some edge case in the protocol through their attack, for example. Yeah.
Oh,
Go ahead.
no. Next
Okay,
question.
okay.
Next
So
question, yeah.
the next question is, does East Shadow support logging capture?
Yeah. I would like to answer this question so much that I think this is an important thing that I didn't mention in the presentation. Like, you can see every SCD out like of every node, every process, and like you can also see like SCD out, SCD error, and you can see every file that the clients produce like in every node. Yeah, that's quite cool.
Okay, cool. We have 1 more minute for Q&A, so please keep the questions flowing in. The next question is, do you support DVT such as SSV or OBOL, I guess? And what about eigenlayer AVS?
Not yet. I mean, theoretically, you could configure it kind of yourself. However, it's likely that those clients also won't work within Shadow without some added work in Shadow. Yeah.
Okay, 30 seconds. Is it complicated to add other clients?
Yes. That's why we hope that we can get the core developer community interested in this, because it's a lot of work, especially in Shadow. So, for example, Teku support Anton Nashaturev from Consensus helped us a lot with this. If you are interested in adding your client or some other piece of software to ETH Shadow, approach us. We'll try to get you started.
All right, so unfortunately time is up. There's a lot of upvotes there. So, one more question then. How do you define the simulation to run? Just submit the list of transactions to the network?
If you want to send a list of transactions, you can do that. You can just spin up a special node and then run the software to submit the transaction to some node, and the transaction will be included on chain and everything, and you can look at everything. Yeah.
All right, so unfortunately time is up. I think Daniel and Pop will be hanging around. So if you have more questions, feel free to reach out to them probably down the stage. For this session, thank you so much, Daniel. Thank you so much, Pop, for the session.
Yeah, thank you so much.
Yeah.
Thanks.